a man who needs no introduction, Professor David Sedlak. He's going to get one anyway. He's the Plato Malozemoff, I'm sorry about that last name, professor in the Department of Civil and Environmental Engineering at UC Berkeley, and the director of the Berkeley Water Center, and known as the author of Water for All, Global Solutions for a Changing Climate, and Water 4.0, the past, present, and future of the world's most precious resources. When you investigate many of the innovative ideas that we've talked about, I mean, like, for instance, Jackie Zipkin was talking about the Hayward horizontal levee, you find the fingerprints of Professor Sedlak. And he's generally behind or involved in a lot of the thinking behind a lot of the good stuff going on. So really, without further ado, apologize for the lateness. Here is Professor Sedlak.
Let me pull this up here. So thank you very much for the introduction, Dennis, and for inviting me to be here with everyone today. It would be great to see you all in person, but this is the next best thing, seeing you virtually and having a chance to talk with you. And I welcome any questions you have either afterwards or even get in touch with me after this talk, or if you're watching it recorded at sedlak@berkeley.edu. So as Dennis said, I am a member of this Bay Area water community, and I think that the Bay Area water community has shaped me, has changed me, and continues to inspire me. And so when times are tough and it looks like the world isn't going anywhere, one of the reasons that I take solace and have a certain amount of optimism about the world is seeing all the interesting projects going on in the Bay Area and in the Bay Area water community, and thinking about how we're going to try to move ahead in the future. And so rather than talking about some of the work that I've been involved in the Bay Area today, I want to take a step back and consider like a bigger picture. I want to think about the longer term vision of where not only the Bay Area cities are going with respect to its water supply and water sustainability, but the state of California, the United States, and the entire world. And I want to try to do that through the lens of this new book, Water for All. But I also want to do it with examples from California. Some of the examples are from the Bay Area, some are from Southern California, some are from the Central Valley, but it will give you the idea about why I am so inspired to be a member of the California water community, and I think how the ideas that we pioneer here in California have the potential to spread around the world and lead to a lot of positive change. So my experience in working with water and kind of maybe having this bigger view were formed when I started to sit down to write Water 4.0, this book that came out about 15 years ago. But they started well before that, when I became involved with the issue of water reuse in Southern California and had a lot of opportunities to talk to members of the general public about what was going on with their water systems. And I was always somewhat surprised at how little not only members of the public and elected officials knew about the water system that we've inherited over the generations, but even how many people who work in water as a profession don't have a full understanding of how we got the system that we ended up with. And so that's part of the reason why I wrote Water 4.0, was to tell the story about the way in which water systems develop, the way in which they can't meet the challenges that the future throws at them, and the way in which they rapidly undergo a period of change. And this idea was that water systems seem like they're not susceptible to any kind of change. They're really stuck in their way. They're unable to do what we want. But suddenly, when a series of actions that feel like catastrophes or at least real big challenges happen, the better ability of people to become creative and pioneer new solutions leads to a rapid period of change and a new system. And that experience of writing Water 4.0 and talking to people about their individual experiences with rapid change made me realize that the book that I'd written, Water 4.0, was about water in wealthy systems in dry places of the world. And I wanted to think a little bit more broadly about the larger water challenges that the world faces. And that's really what I've done in Water for All, a book that came out about a year ago, and which takes a broader view, especially thinking about the way in which climate change is affecting the world's water system. So I want to spend a few minutes just kind of giving you the framework of this larger idea of the book Water for All, and then turn to California to show you some of the examples of what I think is coming down the pike, the kinds of new technologies and new approaches that we may be looking at in the coming decades. So if we think about water and water development issues at a larger scale, we can't do this without first thinking about the Anthropocene. So I think most people who are attending the meeting are familiar with this concept of the Anthropocene. I think the Anthropocene is a great way of thinking about it, but I also like the framing of the Great Acceleration. And the Great Acceleration is this idea that in the period starting right after World War II, the second half of the 20th century, we saw a variety of major changes worldwide. And these 12 images here, which are like a classic analysis of this, are just some of the many images that one could show to illustrate what happened in the second half of the 20th century and is still happening today. Obviously, population grew very quickly. People migrated to cities. The GDP of the world started increasing, and the result was a large increase in the amount of energy we used, large increases in the amount of fertilizer we consumed, a period in which the world was building large dams, and an increase in water use. And that idea of the Great Acceleration has been underlying a lot of the changes that we see in the world. And we think about the stresses on water systems, a lot can be explained by that. The other part about this figure, if you look a little more carefully at the different shades of this red-orange color here, is that it differentiates between the OECD countries, that is the wealthy countries in Western Europe and North America, Japan and Oceania, and also the BRICS, Brazil, Russia, India, China, and South Africa, that have undergone a period of rapid growth recently. And then the others, primarily Sub-Saharan Africa, South America, and parts of Southeast Asia, that have yet to undergo some of that economic transition. You can understand that we have, in some parts of the world, increasing demands for not only water and places to live and cities, but also the production of more food. And then we also see that in the OECD countries, a slowing down in growth, and even in some of the BRICS, a slowing down in population growth that's going to affect the way water systems develop in the future. So an example of how this plays out is that in the second half of the 19th century, London was the fastest growing city in the world, and it doubled in population about every 60 or 70 years. In the 1970s and 1980s, Los Angeles or Southern California was one of the fastest growing places in the world, and its population was doubling about every 30 years. Today, the 10 most rapidly growing cities in the world are in sub-Saharan Africa, and they're growing, doubling in population about every 10 or 15 years. And so you could imagine if you're a city in one of those parts of the world that's growing that quickly, the kind of slow development that we had even in the second half of the 20th century isn't enough for you. When you build out your water supply, when you think about providing enough food for people, you have to do things much more quickly, and the slow, deliberate process that we've become accustomed to doesn't quite work. So there are a lot of challenges to understanding the needs for water supply in low and middle income countries that become more clear when you think about the pace of change going on. The other underlying driver of change and a need to think differently about water that I develop in the book is to think about climate change. And I think many of us here have been thinking about climate change for many decades. but not really having a full understanding of what climate change has meant to water supplies. And I think the thing that's made it most clear to me, or that was most striking to me as I took stock of what kinds of factors associated with climate change are most likely to affect the way we source and use water, is to think about the expansion of the thickness of the Hadley cells, or the width of the Hadley cells, as the planet warms. So you may have seen a figure like this in elementary school or in high school, or maybe a freshman class in college, showing the ocean circulation patterns and the air circulation patterns on the Earth. And the important part here is that at the equator, there's this zone, the equatorial region, where you see a lot of air, a lot of water evaporating into the atmosphere, and that leads to the wet conditions near the tropics. That goes up into the Hadley cells at the equator that go north and south from there. And when they come back down at about 30 degrees north and 30 degrees south latitude, the air is quite dry. And that's why we have the great deserts of the world, like the Sahara Desert or the Kalahari Desert, at 30 degrees north and 30 degrees south latitude. Now, as the climate warms, we're going to see the Hadley cells expand in size. And so the climate of North Africa is going to become the climate of the southern Mediterranean, and the climate of northern Mexico is going to start to become the climate of Southern California. And all of these changes will lead to a great water scarcity. This kind of water scarcity that we are expecting as a result of higher temperatures and the change in ocean circulation patterns is predicted to result in a decrease in precipitation of about 10 or 15% in that zone right adjacent to the Hadley cells. And that may not sound like a lot, but you have to accept the idea that this is accompanied by increased rates of evaporation, or a process known as aridification. And the best place to understand this is to look at Perth in Australia, where, due to changes in the local conditions in the Indian Ocean, they're already seeing a decrease in precipitation of about 10 to 15%, the amount that we'll expect as the climate changes over the next 30 years globally. But Perth's water supply has decreased overall by more than 50% as a result of that warming. And it's a combination of less precipitation and hotter, drier conditions leading to more evaporation and evapotranspiration in the watersheds. And so in Perth, they've already become a leader in seawater desalination and water reuse in a very short amount of time, because there were no other options for a water supply. And we're going to see those kinds of changes throughout the world, especially on the edges of the Hadley cells, where this process of aridification is going to become more intense. And we're already seeing that in our Colorado River basin in the American Southwest. So Water for All thinks about this, and thinks about the separate water crises that are likely to drive change. And because these changes are so different in different parts of the world, I've chosen to break up these water crises into 6 separate crises. The first one in the top left is water for the wealthy. You can see here a picture in the background of the seawater desalination plant in Carlsbad, north of San Diego. And that's the kind of solutions that people who live in the wealthiest cities in the world can pursue. We can build seawater desalination plants, we can engage in water recycling, and this is kind of our way out of crises. But the majority of people in the world don't live in wealthy cities. There are about 1 billion people who live in the wealthiest parts of the world. There are about 1 billion people who live in the poorest parts of the world, and everyone else is somewhere in between. And I refer to that as water for the many. And you can see in this picture here, a water operator in Manila in the Philippines opening and closing valves to allow water into different parts of the distribution network, because they're unable to maintain pressure in the water system 24 hours a day, seven days a week. And that's part of the problem of water for the many, is that building water systems that can deliver an adequate supply of safe water. And that's a lot different than the systems we're familiar with in the wealthiest parts of the world. And this is distinguished from the third type of water supply crisis that people face, and that's water for the poor. And that's the depending who you talk to, the close to 1 billion people who obtain their water from unimproved sources, whether that's buying water from a truck, go walking long distances to haul water back home, or using an unprotected well. But there are three other crises that I examine in some detail in the book. The fourth one is water for health. And you can see here a picture of a woman pumping a tube well in Bangladesh. And many of us are familiar with the idea of the mass poisoning that happened in Bangladesh when people chose to move from surface water supplies, which were contaminated with waterborne pathogens, to shallow groundwater, which turned out to be contaminated with arsenic. And dealing with that issue of a local water supply that has a geogenic element like arsenic or fluoride in it is a real challenge, not only in low-income countries, but also even in wealthy countries, where when we have arsenic in a groundwater system for individual homes in the American Southwest or in Chile or some other part of the world, it's even a challenge for us with our much greater level of resources. And that's not even to start talking about the water contamination issues associated with things like PFAS, which we have a lot of time to talk about, obviously here in California. The fifth of these crises is water for food. With the growing world populations, the increasing wealth, and the ability of people to afford to eat higher on the food chain, coupled with aridification, we're going to have to grow something like 70 or 80% more food by the year 2050. And we're going to do it probably on about the same amount of land. And the way in which we're going to do that is we're going to intensify agriculture. Many people think about going through a second green revolution to increase crop productivity. And with that is going to be the need to obtain and use water more effectively on farms. And you can see a picture here of flood irrigation in California's Central Valley. Yes, we still have places where we flood irrigate crops. It's the main way irrigation's done worldwide, and we're going to have to move away from that in the future. And finally, the last of these is water for ecosystems. So picture, you can see a satellite image from NASA of the Aral Sea in Central Asia drying up over time because its source waters have been redirected to agriculture, but these inland terminal lakes are just one symptom of a larger problem with humanity's control of water, not only water quantity, but water quality, leading to things like dead zones, leading to things like decreased flows for ecosystems. And so you have these 6 separate but interlinked problems that I try to explore in the book and give some ideas about how technologies will cross over from different areas and lead to problem solutions, and how a combination of technological solutions and policy solutions and changes in the way people view water can be instrumental to solving these problems. Now, I don't have time to go into all of these different crises today in any level of detail, and I also think the people who are here at Waterpalooza are a little more interested in local water issues. So I want to try to apply the kind of thinking that I describe in the book to California. And I want to talk primarily about 2 of the newer approaches for meeting California's water security needs, water reuse and desalination. So let me start by talking about California's water reuse revolution. What I plotted here is some data from the State Water Resources Control Board. And what I'm showing is that in the dotted line at the top, the volume of municipal wastewater, water flowing out of our sewage treatment plants in the year 2020, and I'm plotting from the year 1970 to the year 2040, the fraction of that, or the amount of water that's actually been recycled in some fashion or the other. And I've done it for different regions of the state. I've separated the Central Valley from Southern California, and I'm showing the San Francisco Bay there as well. And I want to differentiate between 3 different periods of water reuse in California. The first period is a period from about 1970 to 1990, when the majority of our water reuse was non-potable or for agricultural purposes. And you can see that the majority of the wastewater reuse took place in the Central Valley or perhaps in the Salinas Valley, where water was used on crops or pastures. And that was and then we had purple pipe projects delivering recycled water to things like ball fields and golf courses. In the period from, in the period from 1990 to about 2010, we saw the growth of indirect potable reuse, this idea that you could take wastewater, put it through advanced treatment processes and put it back into the ground, returning it to your water supply. This is probably best known for the case of Orange County and the Orange County Water District, but we also see this in places like West Basin and the Inland Empire, where a lot of investments were made in indirect potable reuse. And then a period from about 2015 or so to about 2040, if you can trust the plans that have been published by different agencies, where we have a combination of indirect potable reuse and direct potable reuse, where we're likely to get to a point where about 2/3 of the wastewater in the state is recycled in some way or another. You'll notice if you look a little carefully that the San Francisco Bay is a relatively small contribution here. It's the solid blue line here halfway through the figure. And I think we'll hear tomorrow from Hussein about the Santa Clara Valley and other projects that might increase that number. But where we sit right now in 2024, we're not expecting that much more potable water reuse or reuse in the Bay Area to come about. And we could have a lot of discussions later about why that's the case. But that is only the first stage. I think that we will be at a point in 2040 or 2050 where all of the big centralized water reuse projects that can be built will have been built already, but there's still time for another water reuse revolution. And that next revolution, I think, is going to happen at the building or premise scale. So whether it's an individual building, a housing development, an office park development, I think what we'll see next is an increase in the amount of water that's recycled without ever going to the sewage treatment plant. And the inspiration for a lot of this surprisingly comes from projects outside of California and from places where water scarcity wasn't the driver. This particular project here, Battery Park City in New York, is a great example of something that was inspirational to many of the engineers here in the Bay Area. It's a development in Lower Manhattan that houses about 10,000 people and serves about 35,000 other people a day through various facilities, commercial and office facilities. And they recycle about half of their wastewater. So you can see this process schematic in the background showing that wastewater from produced within the buildings gets used for cooling water, gets used for laundry water, gets used for flushing toilets, and even gets used for outdoor irrigation. The motivation for this project was they wanted to reduce the amount of water flowing into their sewer systems during rainstorms to minimize the amount of combined sewer overflows. But in the process, they got to a point where they were capable of recycling about half the water in the buildings at the building scale. And because the cost of water in New York is relatively expensive, by the time you factor in the subsidies and incentives that the New York Department of Environmental Protection offered to the building developers, the return on investment for the project was less than 10 years. So it looked very attractive. And I think this is one of the inspirations that has driven San Francisco PUC to implement its on-site reuse projects that you can see here in the background. So the folks at SFPUC have had a wonderful program where these large, iconic projects built in the heart of San Francisco over the last 15 years or so have been required to either have some form of rooftop rainwater capture and reuse or in-building water recycling. And we're seeing somewhere around 45 projects that have been permitted and about 30 more that are currently under planning. And these projects take water that falls that's produced in the building and uses it inside the building. And they're kind of similar to the ones in New York. They're getting the water for things like toilet flushing and cooling towers, and that's been pretty good. But I think that where this is going to go in the future and where it could be even more impactful is if we could find ways to treat this water to the point where it's of potable water quality and we could reuse it in the building itself. And it fits into a larger vision of our buildings being active parts of the water system. One of the drivers for this, in my opinion, is that we could make the water coming into our buildings more healthy for us. This figure here from a report that the National Academies put out a couple of years ago is talking about the risks of Legionella, the bacteria responsible for Legionnaire's disease. And a lot of times it's harbored in the pipes within a building. And it's because those pipes don't have a sufficient circulation of water and sufficient water quality. Similarly, when we think about the disinfection byproducts in our chlorinated water, a lot of people maybe think about avoiding their tap water because they're concerned about exposure to things like chloroform and other types of disinfection byproducts, but they don't recognize that they're being exposed to many of those same disinfection byproducts when they bathe or shower in this water. This figure here from a study conducted by the EPA and Research Triangle Park shows the blood concentrations of chloroform before and after drinking tap water that had chloroform in it from chlorination, but also from bathing or showering in that same water. And you can see that taking a 10-minute shower in chlorinated water gives you, in many cases, a higher blood concentration of chloroform than drinking tap water that has the same sorts of disinfection processes. And I think there's a possibility to make the water coming into our buildings and to make the pipes in our buildings safer by thinking about the buildings as part of the treatment system. Part of my inspiration here was my youth growing up just outside of New York City and seeing wooden water towers on the roofs of buildings and realizing that those things were in some ways like a bladder for a building. They were storing water and releasing it into the building. And while the water's sitting there in that bladder, there might be an opportunity to filter it or treat it in some way, or to think about that as an opportunity for the building's liver to detoxify it, or to think about the plumbing system in the building as a type of circulation system, or the control system for the building being like a brain. So in some of our research, we've been thinking about ways to use fully electrified electrochemical water treatment systems to improve water quality, that you might be able to stick a simple device that's powered only by electricity into one of these water tanks or into the flow of water in the building and remove some of the contaminants that pose public health risks, or remove some of the waterborne pathogens. And there are many examples that we're seeing increasingly from the stormwater control area where controllers and sensors can be used to operate buildings much more precisely than what we're doing today. The other aspect of using buildings as part of a treatment system is that it feeds into a larger vision of how water could be a key to green development. One inspiration here that we can look towards are the so-called super blocks of Barcelona, where people are thinking about ways of taking blocks of apartment buildings and making them kind of a hub for better ways of living. And we completed an analysis of buildings like these in 2024, where we did a techno-economic analysis of the cost of putting in-building water treatment systems that harvested the nutrients from the wastewater and used them for vertical farming on the sides of the buildings, and then sold that the fresh fruits and vegetables produced in those systems to local residents. And like the system in New York that we were looking at, we saw a return on investment of less than 10 years. And these are the kinds of things that I think could garner a lot of public support because they feed into a larger narrative of green living. We've also looked a few years ago at the cost and space requirements for in-building water recycling systems that could meet the entire needs of a building. We've thought about so-called net zero water buildings, where through a combination of things like membrane bioreactors in the basements of buildings and advanced treatment systems and possibly rainwater harvesting, you could provide all of the needs for a city's a building's water supplies. And when we cost it out, we get to something like $1.5 to $2.7 per cubic meter, which puts it in the same sort of cost range as modern seawater desalination systems in the United States. But the difference here is that that's the price that's paid by the occupant of the building, not the price that's paid on the water bill. It turns out that by the time you add up everything else that involved in the water supply, water is actually quite a bit more expensive than that. So we get to a situation that looks like the early days of rooftop solar, where if you allow people to install in-building water recycling systems, they will find it economically beneficial as long as you don't charge them a large hookup fee. And because this kind of technology would scale slowly, we don't think it would have a huge impact on municipalities' bottom line of its water, of its ability to provide services. So you could have a small number or a modest number of so-called free riders having their own in-building water recycling system, but relying upon the centralized utility for extra water, for firefighting, for example, or for periods of drought. And that would allow a city to start transitioning or diversifying its water supply with building scale water recycling system and not having to rely upon dual reticulation plumbing where you have to retrofit a building with two types of pipes. So as I think about the future of these premise scale water systems, I think that they do have applications in places like San Francisco and other big cities, but perhaps their big applications will happen elsewhere. And the wealthy cities in places like California might just be the laboratories where they develop their economies of scale. And I could see applications in places like single family dwellings. We have a lot of places in the United States where individual homes don't have enough access to groundwater, for example, or are suffering from water scarcity due to drought. Rooftop rainwater harvesting and water recycling in a home could allow people to live in places where the local water supply is inadequate. We could look to places like Allensworth, south of Bakersfield, a community where the local farms had pumped so much groundwater that the residents no longer had access to a water supply and had to rely upon trucked water being brought in. And we can also think about some of those emerging megacities in sub-Saharan Africa and South America that I talked about earlier, where instead of building out their water infrastructure like we've done here in North America or in Western Europe, they might look to these kind of small scale building scale systems as the way to go. And we already see signs of that happening in places like Bangalore in India, where there's a requirement for new buildings to have in-building water recycling. And residents are starting to see that as a feature that they want in their buildings because it means they'll have reliable water service. I want to turn my attention now to the issue of desalination in California. We don't talk a lot about desalination, especially here in the Bay Area, and that's because we don't really have a lot of it. This study that came out from the Department of Water Resources recently showed the locations where we have desalination as a water supply, and right now we have somewhere around 43,000 acre feet per year of seawater desalination capacity in California. That, if you think about that, that's pretty small compared to the 700,000 acre feet per year of water reuse that we have. So it's less than about 5%, or it's about 5% of the water reuse capacity we have. So that's part of the reason why we don't talk about it. But the other reason we don't talk about it is that there's been a lot of opposition to it. So you may be familiar with the proposed project in Huntington Beach in 2022, which was rejected by the Coastal Commission. Or maybe you've heard about some of the controversies associated with the proposed plant in the Monterey Peninsula area, or you know something about the continued opposition to the treatment plant or the desalination plant in Carlsbad, which is still, even though it's operating, a source of a certain amount of controversy. And so if I had to pull out that magic wand, or that maybe along with the magic wand, a crystal ball to tell me about where I thought seawater desalination would go in California in the next 20 years, I'm not expecting to see many large seawater desalination plants. We might get a few small ones like the one that was built in Santa Barbara. But I think the real opportunity for desalination in California is small desalination and treatment of brackish groundwater. And we heard a little bit earlier about how everyone was surprised by the project being run by the Alameda County Water Agency. But the real place where we're doing a lot of brackish water desalination is in Southern California. And I just wanted to give you these two examples of the brackish water desalination plants north of Los Angeles and the Oxnard Plateau, including like the Oxnard desalter shown in this image here, and some of the statistics about it in the text in the middle, and also in the Inland Empire area, where I'm showing the Eastern Municipal Water Agency as an example. And what you can see is that they're producing water which has a cost of about $1,000 an acre foot. So it's kind of in the same range of cost of potable water reuse and desalination, but it's happening because it happens in a small local area. And in both cases, this has been made possible by the existence of brine lines, that is, pipelines that are able to take the salt that's produced by the desalination process and release them back to the ocean. So there's a brine line. You can see the green line here on the right-hand side in the system in the Oxnard area. And then you can see on the left-hand side, the Inland Empire brine line, which has been key to the success of the desalters in places like the Eastern Municipal Water Agency. So when we're able to find a way to get the waste from the desalination process, that is the brine produced by desalination, back to the ocean, these become very attractive and cost competitive. In fact, in 2016, a consortium known as CV Salts, the Central Valley Salt Salinity Alternatives Long-Term Sustainability Program, proposed with a consultant the construction of a 280-mile-long pipeline to take brine produced by a group of over 30 desalination plants and move it up to the San Francisco Bay Area, where it would be hooked into East Bay Mud's outfall or some other way of getting it to the ocean. And that project would have cost somewhere around $11 billion. And the cost of water would be about 3 times as high as those projects which I showed you a few minutes ago. And so obviously this isn't the kind of project that's likely to be built. And part of the reason that this project is unlikely to ever be built is the high cost of dealing with the brine. But to me, what it showed was that there's a recognition that there's this resource of salty or brackish groundwater that is underexploited. And also, as more salinity problems arise due to the way we use water for agriculture in the Central Valley, there's going to be a role for desalination in the future. And so we've looked a little bit through the National Alliance for Water Innovation, a Department of Energy program, at this issue of alternatives to brine lines. And this is a figure that came out of one of the papers that we produced through NAUI a couple of years ago, looking at the possibility of using so-called zero liquid discharge, this idea of taking the brine from the desalination process and drying it, and then putting that crystallized salts and disposing of it in some way or another. And what you can see is that the existing types of ZLD or zero liquid discharge projects, A, B, and C here, can increase the cost of these projects by anywhere from about 25 to 75%. But I think that initial analysis probably underestimated the cost of disposing of the brine. Right now, a lot of desalination projects that use zero liquid discharge simply send the salts to a landfill. And in the long term, that's just not going to be a feasible way to go. So we really have an issue with this question of brine disposal. I'm going to move through these slides and talk about really what I wanted to talk about with respect to brine disposal is the idea that if we could take the brine produced by desalination and make it into a valuable product, that's what people refer to as brine valorization, we might have a way of taking advantage of the relatively low cost of brackish water desalination and converting this waste not to a pile of like undifferentiated salts, but to valuable products that could either be used by industry or by agriculture. And one of the inspirations for this was a project that started at the K. Bailey Hutchinson brackish water desalination plant in El Paso a few years ago. A small company called Environmental Water Minerals had a proposal, and they built a plant that took the salt produced by that brackish water desalination plant and produced caustic soda, sodium carbonate, hydrochloric acid, gypsum, and magnesium hydroxide, all products that are commonly used in industry, with the idea that instead of having to pay someone to dispose of the brine produced by the desalination process, you could sell it into industry. That company, EWM, was not successful in terms of their projects, in part because they came into the design process so late. But as part of the DOE's NOWI program, we've funded a project where we're looking at ways of improving the technologies for valorizing the brines from desalination plants. And we're starting to look at the techno-economic analysis of this and the technology feasibility. But my prediction is that in the long run, rather than thinking about desalination and the brines produced by desalination as being a source of waste that has to be piped to the ocean, we're going to start looking at it as a source of products that we can use. And in the case of agriculture, many of the things that we take out of this brackish water brine, whether it's potassium or magnesium or sulfate, are all used by in agriculture as fertilizers. And so not only are we producing things like caustic and sulfuric acid, we're producing gypsum and potash, which can be used in agriculture. So thinking about like this original proposal that CV Salts had, which is likely a non-starter, and thinking about the high costs of water that farmers, especially in the southern part of the San Joaquin Valley, are already paying for water, especially when they use it to grow high-value crops like nut trees or fruits, and thinking about the possibility of building small desalination plants where water could be desalinated as needed in small locations where this high value agriculture takes place. We're starting to see the outlines of spread of desalination into agriculture, where in the initial years, salty water could be desalinated, allowing it to be used to grow high value crops. And the brine produced in the process could be valorized and turned into fertilizer, or at least the volume of waste that would have to be disposed of would be small. And this would allow an industry to start to grow and drop the cost as more and more people become familiar with it and start to adopt it. This idea of thinking about desalination and also to another degree reuse and its role in food security is starting to catch on beyond just ideas in California. Last spring, the UN Food and Agriculture Organization held a workshop in Rome looking at this idea of brackish water, or rather of desalination and its applications in agriculture. And I was, as a member of that workshop, I was quite impressed by the projects already taking place in places like Spain and North Africa, where desalination is starting to be used for high value crops. So thinking about like this idea of these new technologies like direct potable reuse and building scale water recycling and desalination of brackish water followed by valorization, I like to take inspiration by thinking about the history of solar voltaic power. So I'll take you back to 1976 to Jimmy Carter being president in the White House. And maybe some of you remember when Jimmy Carter had the solar panels installed on the roof of the White House. And maybe some of you also remember how when Ronald Reagan became president, he had the solar panels pulled off the roof of the White House. Well, I think Jimmy Carter had the last laugh, because in the years since 1976, the cost of installed solar production has dropped by over 2 orders of magnitude. And now the idea of rooftop solar panels has become commonplace. And we can see the same sorts of things have already started to happen in desalination. You can see the figure on the left is the same sort of plot as what I showed for photovoltaics of seawater desalination plants and their costs dropping as more capacity is built. And also you can see on the right this kind of prediction, which is more like an artist's view of what the price of seawater desalination has done since about 1970. And I think that we can say safely that the cost of seawater desalination may bottom out, but those other technologies that I talked about earlier, they're in their infancy, and we could imagine them dropping in cost by orders of magnitude over time if we are willing to give them an opportunity to develop and to grow and possibly even subsidize them in the early years. So a few takeaways from maybe the larger view that I try to relate in Water for All. First of all, I told you a little about these 6 global water crises. I think that they're all going to become more prominent in the coming decades as the impacts of population growth and climate change become more extreme. I don't think that there's any one solution to the world's water crises. I gave you kind of a view today that that is a little bit more technology heavy. I think there's lots of room for policy solutions too. I think there are a lot of bad policies out there that if they were corrected would help us solve water crises. But I wanted to give you kind of a view of some of the technologies that were around the corner. These technological solutions, as I was saying, are going to continue to decrease in cost over time. And the technologies that are developed in some wealthy countries, especially here in California, have a lot of potential to spread to other places, just like solar panels and cell phone technologies, and many other ideas have spread to other places. And finally, I'd like to end with this idea that really the view of having a shared stewardship of water, and I think that's really the view that I appreciate so much from Actera and that so many of the participants of Waterpalooza share, is that we have a shared responsibility for water. And I think that that's the only viable path for us to get to water for all. And with that, I'll stop sharing my slides and welcome any discussions or questions that you might have.
Well, thank you, Professor Sedlak, for a masterclass on just a lot of issues. I mean, certainly I made a number of notes, a lot of things to kind of follow up on. There was a question about growing up in Europe, where generally water is not chlorinated, just filtered. Are most agencies in the US just driven by the higher cost of adequate filtration to remove pathogens? And I will add this, that's chlorination. I would add, perhaps you can address the fluoridation. We're back to that old movie, Dr. Strangelove, and we're talking about fluoridation these days too. So if you could address the dations.
Okay, well, first of all, I'll say that there are parts of Europe where water is not filtered. For example, I think Denmark is a good example of that, where people rely upon groundwater, and groundwater in many cases can be delivered without filtration. But many parts of Europe that use surface water still rely upon either chlorination or ozonation as a primary disinfection. And then there's a secondary disinfectant that we add to water here in the United States, and that's chlorine. And we could have a long discussion about why there's more of a need to add chlorine when we send water into the water distribution system here in North America than there is in Europe. Our cities tend to be larger, our water distribution systems are longer, so the water spends more time in them. We also do a worse job maintaining our water distribution system, so there's more opportunities for the water to get recontaminated after it leaves the drinking water treatment plant. And so there probably are some cities with an investment in the United States where water could be put in the distribution system without chlorination, but in our current state, we need some sort of residual disinfectant, whether that's chlorine or chloramines. And then when you talk about Europe, Europe's not a monolith. You have the Southern European countries, which are quite different from Central and Northern Europe, where they often use practices very similar to the United States. And so I go into it a little bit in the book, but that's kind of kind of a little bit idiosyncratic, but our chlorine in our water and our residual chlorine is there to protect our health. And in most cities, we couldn't get away without it. Fluoridation is really an interesting one. I think I have kind of an evolving view on it, and I'm still not sure, because if you look a little carefully at this recent health effects study that the government put out on fluoride in drinking water, there are open questions, and I think there's some science that needs to be done about the long-term safety of adding fluoride to water. And I never thought I would say that before, but I think it's becoming more and more clear over time. And there are wealthy, progressive countries in the world where they don't necessarily add fluoride to the water supply, but children's dental health is taken care of by, for example, providing fluoride rinses in the schools and things like that. And people seem to do fine in terms of cavities. And so I think we'll have more discussions about fluoride in our water supply in the US in the coming years because of the new administration. But I think those are probably worth having, and it's probably worth having some better research before we start making decisions about what to do.
Oh, so you're talking about educated decisions. Okay, well, that'd be good to try. I wanted also to bring up a question Gita Dev had about habitat problems releasing brine into the bay or ocean. Now, obviously, those are two completely different things. But are there harmful effects? I mean, creating dead and dying zones.
Sure. But in the book, I talk about this in some detail. I think the place where this has been best studied is for seawater desalination plants, where seawater desalination plants take in seawater and they release water that's about twice as salty as seawater. And those systems are designed where the salt plume should mix into the ocean because there are diffusers used. And within, what is it, 10, 50, 100 meters of that mixing point, you shouldn't be able to detect a difference in the salinity versus the salinity of the ocean at large. So you don't really see problems with a properly designed seawater desalination plant until you have a lot of them. So there's some concern that in parts of the Middle East where you have many seawater desalination plants on a small, shallow ocean or embayment with currents like the Arabian Sea, the ambient salt concentration may go up, and that could pose risks to the ecosystem. But in places like Southern California and Australia, the modern mixing systems for those salt plumes should, in theory, protect the ecosystem from the salt problem. With respect to brackish water, that brackish water has got a different composition than seawater. And so when you take the brine from brackish water desalination and mix it into the bay or the ocean, you have to be very careful. For example, if you took brackish water brine from the Central Valley and mixed it into San Francisco Bay, you'd want to be very careful about the selenium levels, because selenium, we know that we have selenium in the drainage water from the Central Valley, and we know that many aquatic organisms and seabirds are affected by selenium. So you might have to do treatment to remove the selenium. And so you might need either more and better dilution, or you might need some sort of treatment. And I guess the Inland Empire brine line, which is a relatively large brine line that operates in Southern California, has evaluated some of these things, and they do think about those kinds of impacts. And to date, they haven't seen any signs of trouble. But I think that each one has to be evaluated on a case-by-case basis.
I was thinking when we're talking about relative levels of salinity, that a lot of the like tertiary treated water, kind of the standard water treatment that then goes into the bay is fairly high in salts. I mean, you had mentioned 800, I think it was 800 milligrams at TDS as being a top area of level. And so they may be up around that level, but it's still less salty than the bay water.
Yeah, I don't think the wastewater discharges or the brine produced by water recycling, for example, I don't think the salinity is the issue there. I think there it's the case of like nutrients or some sort of trace contaminant. The salt issue really gets to be much bigger when you talk about brackish water desalination and these high recovery desalination systems that they use.
You mentioned Hussein Ashgrab. He's on tomorrow, and something that popped up recently has been, I guess, desalination from bay water, but it's non-brackish, I guess. So it's closer to ocean desal, I would think.
Well, I mean, historically, desalination of San Francisco Bay water has been kind of like a third rail of San Francisco water issues. No one wants to think about sticking a pipe in the bay and desalinating water because of concerns about mixing of the brine and possibly entrainment of organisms. And I think that some of the new thinking about uh, desalination in San Francisco Bay would consider things like subsurface intakes, where instead of pumping seawater directly out of the bay, you're pumping the salty water just adjacent to the bay, which reduces the likely impact on the aquatic organisms and makes it more a question of how you would mix that water back into the bay without causing a salt problem. I think that, that's why I don't think we're going to see large seawater desalination plants built in California in the coming years, because there's this historic animosity towards it. Because once upon a time, seawater desalination was a real energy hog. And I think a lot of people still think that. And also a lot of California water people think about the many years that they fought against once through cooling on the coast, and those long wars with the Coastal Commission. And I think it opens up that same sort of thinking again. And that's why it seems unlikely that there's a rapid path to adoption of large seawater desalination plants here.
Speaking of energy usage, there was a question about combining solar with desalination to reduce the cost of desalinated water. I
I
guess that's
think,
more of a
yeah, no, I
local
think
energy.
any desalination project in California these days, there's going to be a push to make sure that it's not increasing greenhouse gas emissions. So it may be like in Australia, the desalination plants were an excuse to push the utilities to build more renewable capacity. So in Perth, they built a wind farm, they built a solar farm to support the new desal plant. So that's a plus there. But directly using sunlight to desalinate water, that was maybe an area of interest for a while, a few years ago, but I think the community is coming to recognize that just decarbonizing the electricity supply and using the electricity for desalination makes a lot more sense, because the sun is only shining part of the day and the intensity goes down at different parts of the year. And so if you build a desalination plant, you have a lot of motivation to operate it all the time and not just in the middle of the day.
Yeah, when you showed the Jimmy Carter era, or the post Jimmy Carter era, and actually I do remember when they installed those panels just as a little kid, and their subsequent decommissioning. But that graph that you showed, which was kind of, a Moore's law graph, was also a graph for battery storage and, prices as well. And yeah, so hopefully there's some economies that can be used in that.
That idea shows up over and over again, whether it's civil aviation, whether it's automobiles, any new technology. There's a logarithmic relationship. The more units you build, the more you learn by doing, and the more economies of scale you get, the more the price drops. And so the thing we have to remember is that water projects also have financing and regulatory compliance, and those things are hard to get the same sorts of economies of scale from. So eventually they level out and flatten out a little faster, I think, than some of the rooftop solar does.
There's love expressed for the idea of valorization.
Yeah,
And
I hope we can do it. I think that, realistically, we can't valorize 100%. There really isn't a huge market for table salt in the world. But if you can valorize lots of things, the stuff that's left over may be a lot more benign than the salt you had originally. So I'm happy for it, and it's an area of research effort from this Department of Energy NOWI program that I've been involved in, and many others are getting interested in it in the in the startup world, because it has a lot of potential.
The not so much love expressed for the biotech industry and in terms of labs and but I don't know if there's anything you want to discuss on that.
I'm not sure what you mean, Dennis.
Yeah, well, there were some questions and just in the Q&A about um, biotech and I guess releases of biological toxins.
Oh, sure. Yeah, no, I could see that. I mean, basically, when we talk about water recycling, we have to realize that it's more than just you and me using that sewer. We often share that sewer with industry or commercial ventures, and we have to make sure that there are not things in the recycled water that we can't remove. So that's been an area of active research over the past couple of decades, and we've been thinking a lot about that. I would be cautious about putting a potable water recycling facility in a city that had a lot of biotech, for example, like, I don't know, Vacaville or something like that, where a significant fraction of the wastewater is coming from biotech. But that applies to other industries as well. I don't think I'd want to think about a potable water recycling facility if I had a plant that was manufacturing PFAS in the sewer shed. I'd want to make sure that they were doing a good job removing that before discharging their waste to the sewer. And that's an issue that's coming up now as more battery manufacturers and semiconductor manufacturers are looking towards building facilities in the US, because many of those industries are big users of chemicals like PFAS. And we want to be sure that those are well removed before we put them into our circular economy and our water recycling systems.
And then, of course, there's all those artificial turf fields in our green and pleasant land where PFAS is added, actually, to the fibers. Eric Rosenblum has some questions about, see if I can
Yeah,
read it.
I can read it. So Eric
Yeah,
is asking about
in the Q&A,
low-cost solutions, for access to water in low and middle income countries. And there are kind of a couple of levels here, Eric, of building scale water recycling in low and middle income countries. One that's proven effective already is just rooftop water harvesting and rainwater cisterns, which are used in many parts of the world, and I think could be safer if they were accompanied by some sort of, I don't know, UV disinfection system or something like that. But I mentioned briefly that I've been inspired by what I've seen coming out of Bangalore in India, where in Bangalore, they put in this requirement that new apartment buildings have in-building water recycling systems. And initially, they were using some pretty low-tech water recycling systems, but the quality of the water was not high enough to reuse in the building, so it was going to the construction industry. But now some entrepreneurs have figured out ways to add on additional treatment modules and make that water sufficient quality to reuse in the building. And perhaps people who live in India are familiar with not being able to drink the water coming out of their tap, and that's why they're more willing to accept it. But I think it's going to be a combination of like creative low-tech solutions like rainwater harvesting and cisterns, and then in other places, adding on final treatment steps. Like in much of the world, people already use under the sink reverse osmosis treatment systems because they don't trust their water supply. And so if you had an in-building water recycling system and you followed that with an under-the-sink RO unit, you could probably make that water pretty safe to drink. Maybe not necessarily palatable, but at least safe to drink.
The taste of water, something else entirely. Well, Professor Sedlak, thank you so much for closing first day one of Waterpalooza and really giving us all a lot to think about. And the book, folks, it's out there. Your leading book purveyors has it. Even locally, I got mine at Kepler's.
Thanks for the plug. I didn't want to have to do that myself.